The universe you see is only one possibility. A single thread in a tapestry far larger than your eyes, your instruments, or even your imagination were built to hold. And yet, somewhere in the mathematics, in the faint radiation of the early cosmos, and in the strange symmetries of quantum fields, there are hints that our universe may not be alone. Hints that reality could be wider, deeper, and more layered than the stars you see tonight. Some theories say there might be countless universes, each with different laws of physics. Others suggest that space itself may branch, divide, or ripple with every quantum choice. And some propose that our entire cosmic story, from the birth of atoms to the shaping of galaxies, is just one outcome in an endless sea of possibilities. Tonight, we drift into that quiet frontier, not to chase speculation, but to explore the scientific ideas that hint at a multiverse. Ideas drawn from cosmology, inflation theory, string theory, and the strange probabilities of quantum mechanics. Ideas that whisper that our universe, vast as it seems, might be just one of many. If this calm journey brings you even a moment of peace, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps keep these quiet stories alive, and it means more than you know. Now we drift into part 1, a slow beginning into the possibility that everything we know might be part of something even larger. Part 1. What does multiverse really mean? The word multiverse sounds fantastical, but in physics it begins with a quiet idea, that the laws of nature we observe may not be the only laws that exist. When cosmologists talk about multiple universes, they are not picturing parallel Earths or alternate histories. They are considering the possibility that space itself may be partitioned, layered, or multiplied by the mathematics of inflation, quantum fields, or higher dimensions. Before we explore the many interpretations, we begin here with what scientists actually mean when they say multiverse. When physicists use the word universe, they are speaking about something very specific, the region of spacetime we can observe, the part of reality whose light has had time to reach us since the Big Bang. Everything beyond that region, anything whose light has not yet arrived, is simply unobservable, but not necessarily non-existent. In a sense, the universe we talk about is already defined by a limitation, a horizon carved out by the speed of light and the age of space. If space extends far beyond that horizon, and if physical laws vary from one region to another, then the idea of a multiverse begins not with science fiction, but with the basic geometry of cosmology. To understand why scientists even consider this possibility, we must step back to the early moments of cosmic history. The Big Bang was not an explosion that happened inside space. It was the expansion of space itself. Every galaxy, every atom, every photon emerged from that expansion, and for reasons we have only begun to understand, the universe expanded far faster than light for a tiny fraction of a second in an event called inflation. That period explains why distant regions of the cosmos look so similar despite being too far apart to have ever communicated. But inflation also leads us to something deeper, the idea that our entire observable universe may be just one region where inflation stopped. Imagine space as a vast field, silent, invisible, and filled with potential energy. Inflation theory suggests that this field did not decay everywhere at once. Instead, it settled at different times in different regions, like frost forming unevenly across a cold window. Each patch that froze could have become its own universe. These patches would be isolated from one another forever, separated by regions where inflation still continues. If this picture is correct, then the multiverse is not an exotic idea at all. It is a natural extension of the physics that describes our own cosmic beginning. But inflation is only one doorway into the multiverse. Another emerges from the language of quantum mechanics. At the smallest scales, nature behaves not with certainty but with probability. A particle is not here or there until measured. It exists in a cloud of possibilities. One interpretation, the many worlds interpretation, suggests that these possibilities are not mere mathematical conveniences. Instead, each potential outcome is realized in its own independent branch of reality. In this picture, The universe does not collapse to one path when observed. It continuously divides, producing new universes with every quantum interaction. This does not mean countless versions of you making different choices. It means that the fabric of reality itself unfolds along many parallel trajectories, each as real as the one you experience now. For many scientists, this interpretation is not a claim of physical universes, but a way to keep the equations of quantum mechanics consistent. Yet, even as a mathematical idea, it reinforces a theme we find throughout modern physics, that reality may be vastly larger, more layered, and more interconnected than our senses allow. A third doorway comes from string theory, a framework that attempts to unify gravity with quantum mechanics. In string theory, the fundamental building blocks of nature are not particles, but tiny vibrating strings. Their vibrations create everything we observe: electrons, photons, quarks, and even the forces between them. But for string theory to work, the universe must contain more than 3 spatial dimensions. These extra dimensions are not wide and open like the ones we move through. They are curled tightly, folded into intricate geometries at scales far smaller than atoms. And each way of folding these dimensions produces different physical laws, different particle masses, different strengths of gravity, different types of matter. This landscape of possible universes may contain more configurations than the number of atoms in the visible universe. Our universe, with its familiar laws, might be only one stable configuration among a vast and silent mathematical library. If the multiverse exists at this level, we would not be alone in principle, though no other universe would ever touch ours. But to truly understand the multiverse, we must address a quieter question. What qualifies something as a universe? For cosmologists, a universe is defined not by its objects or its inhabitants, but by its laws and its isolation. If 2 regions cannot exchange information, not even light, not even gravity, then they are effectively separate universes. They may share a common origin, or they may not. They may have similar physics, or they may be utterly different. What matters is that no signal can pass between them. They exist in complete causal separation, each unfolding according to its own rules. This perspective reveals something important. The multiverse concept is not inherently mystical. It does not require new particles or new dimensions. It begins with a simple fact, that the region we can see is limited. And if the universe is larger than that region, even by a factor of 1 trillion, there may already be countless regions beyond our reach. If conditions vary across those regions, then the multiverse begins not with speculation, but with geography. Still, when we talk about multiple universes, it is natural to imagine far more extravagant pictures. Some imagine dimensions stacked like pages in a book. Others imagine universes colliding like soap bubbles in a cosmic bath. And while these analogies can help visualize the mathematics, they remain analogies. The true structures, if they exist, would be stranger than anything we could draw. Our universe expanded from a single, hot, dense state. But the multiverse, if real, would be a space where expansion never stops, where universes form endlessly, like sparks from a fire that never goes out. To some, this idea feels overwhelming. If there are infinite universes, what does that say about our place in reality? But in the quiet language of physics, the multiverse is not meant to diminish us. It is meant to explain why our universe is the way it is, why its constants allow stars, why atoms form, why gravity balances against expansion in just the right way to create structure. In a multiverse, these features are not rare miracles, they are statistical outcomes, and we happen to inhabit one of the regions where the conditions for complexity arose. Yet even with all these theories, we must be careful. The multiverse remains unproven. It is a consequence of equations, not a measurement, a possibility, not a certainty. Physics demands evidence, and evidence requires observation, something we cannot yet obtain from beyond our cosmic horizon. Still, the mathematics continues to point in the same direction, that our universe may not be alone. And as we drift deeper into this mystery, one question naturally follows. If multiple universes exist, how did ours begin? And what made it separate from the rest? Part 2. Why the early universe suggests there could be others. In the earliest fraction of a second after the Big Bang, the universe may have expanded faster than light, driven by a field called the inflaton. Some models of this expansion predict that inflation never ends everywhere at once. Instead, it produces countless isolated bubbles, each becoming its own universe with its own constants. Ours is just one bubble where inflation stopped. The rest may still be growing beyond our cosmic horizon. To understand why scientists take this idea seriously, we must step back to the conditions of the universe when it was unimaginably young. Not seconds old, not even fractions of a second old, but 10 to 36 seconds after its birth. At that moment, the universe was smaller than a proton, hotter than any temperature that exists now, and utterly dominated by quantum fields we can barely describe. Among those fields was the inflaton, a hypothetical energy field whose properties remain mysterious, but whose consequences seem to be written everywhere in the cosmic microwave background. Inflation theory emerged to explain a puzzle: the incredible smoothness of the universe. Today, when we look at the cosmic microwave background, the faint thermal afterglow of the Big Bang, its temperature barely varies from point to point. The entire sky is nearly the same, differing by less than 1 part in 100,000. Such smoothness should have been impossible. Distant regions of space could never have communicated with each other in the early universe. They were simply too far apart for light, or any influence, to travel between them. And yet they look identical. Inflation solves this elegantly. Before the universe became large, it was tiny and connected. Influences could pass easily from one region to another. When inflation began, space expanded exponentially, stretching this tiny, smooth region to enormous scales. That's why the sky looks uniform today, because every part of it once touched. But the same equations that explain that uniformity also imply something far more radical. Inflation shouldn't stop smoothly or everywhere at once. It should stop in patches, tiny regions where the inflaton field decays and releases its energy as radiation. Each of these regions heats up, forming a universe. But around these patches, space continues expanding at extraordinary speed, creating room for more bubbles to form. This process is called eternal inflation, and if the mathematics is correct, it never ends. Picture it like this: space expands faster than bubbles can collide, faster than light can cross the gaps, faster than boundaries can grow. Each bubble becomes its own cosmos, sealed off permanently from the others by regions where inflation still rages. Our universe is one such bubble. We inhabit a quiet pocket where inflation ended 13.8 billion years ago. But beyond our visible horizon, inflation may be continuing even now, stretching space so quickly that the light from other universes will never reach us. They remain forever out of view, silent, expanding, unreachable. This is not speculation layered on top of fantasy. It is the natural implication of the mathematics behind inflation, born from the need to explain what we can actually observe. Still, to make sense of these bubbles, we must understand what universe means in this context. Each bubble universe would not simply be a region separated by distance. It would be separated by physics itself. If the inflaton decays differently in different bubbles, then the laws of nature, the masses of particles, the strength of gravity, even the number of dimensions, could vary from one bubble to the next. Our cosmos may have the physics we see, not because it is the only possibility, but because it is one of many outcomes of the inflaton's decay. This is known as the cosmic landscape. Not a single universe, but a vast collection of possible universes, each fixed into existence by the moment inflation stopped within it. Even the seeds of our galaxies carry the imprint of this violent expanding process. The tiny quantum fluctuations in the inflaton field were stretched by inflation into ripples in density. Those ripples later became stars, galaxies, and clusters. Every structure we see, every sun, every planet, every atom of your body began as a vibration in that early field. If other bubbles formed with different fluctuations, their structures would evolve in entirely different ways. Some bubbles might never form stars, others might collapse instantly. Some might be filled with nothing but a thin haze of radiation, and some perhaps might host complex structures we cannot imagine. In a sense, inflation does not just make universes, it sculpts them. But there is something else hidden in this idea, something subtle and profound. The expansion of space during inflation happens at speeds faster than light, but nothing actually moves faster than light through space. Rather, space itself stretches. This distinction is crucial. It means no law of physics is violated, and yet the distances between regions can grow so rapidly that no interaction can ever bridge them. Universes become sealed off forever, not by walls or barriers, but by geometry. The multiverse, if inflation is correct, is not a fiction. It is simply the natural consequence of exponential expansion acting on quantum fields. And while this may sound abstract, we can actually see traces of inflation written across the sky. The cosmic microwave background shows tiny variations in temperature, exactly the pattern inflation predicts. The distribution of galaxies follows a statistical fingerprint that inflation also predicts. Even the large-scale flatness of the universe, the fact that space is not curved dramatically, is explained beautifully by inflation. Every piece of evidence we have points to the same quiet truth. Inflation happened, and if inflation happened once, the mathematics suggests it should still be happening somewhere. Some physicists describe eternal inflation as a kind of cosmic tree. Each bubble universe is a branch. The tree continues growing outward indefinitely, producing new branches that never touch. Our branch is just one growth among countless others. Others describe it as a cosmic ocean, with each universe forming like a bubble of foam on its surface. New bubbles appear constantly, while old ones drift apart, unreachable and isolated. But perhaps the most poetic model comes from imagining inflation as a fire. Once ignited, it spreads through space, expanding faster than it can be extinguished. Occasionally, the flame cools in tiny pockets. These pockets become universes. But around them, the fire continues, generating more pockets endlessly. Still, we must remain grounded. Eternal inflation is a compelling model, but it is not proven. We cannot observe what lies beyond our horizon. We cannot see other bubbles. We cannot measure the inflatant directly. Yet every attempt to refine the equations continues to point toward a multiverse, not because it is extraordinary, but because it is mathematically difficult to avoid. Some physicists argue that the universe is too smooth, too flat, too finely balanced to be the result of a single cosmic event. They see the multiverse not as an added layer of complexity, but as a natural outcome of physics-seeking equilibrium. If space can expand, it will. If fields can fluctuate, they must. And if inflation can produce one universe, there is no good reason to think it would stop at one. Whether the multiverse is real or simply a reflection of our equations, it reshapes our perspective. Our universe becomes not the entirety of reality, but one chapter in a larger cosmic story. And as we follow this story deeper, one question rises gently into view. If other universes formed in their own bubbles, could they ever leave traces on ours? Part 3. Could quantum mechanics split reality? Quantum physics says that particles do not exist in one state until observed. They exist in many possible states simultaneously. One interpretation, the many worlds interpretation, proposes that every quantum outcome is realized, each in its own branching universe. According to this view, reality is not a single path, but an ever-dividing tree, quietly splitting with every moment of uncertainty. To appreciate what this means, we must begin with the strange, almost dreamlike behavior of the quantum world. At the smallest scales, matter is not solid, predictable, or neatly behaved. Electrons blur into clouds of probability. Photons travel as waves, yet hit detectors like particles. Atoms vibrate not in exact positions, but in superpositions, states where they are many things at once. These are not metaphors. They are the results of experiments repeated millions of times. The The famous double-slit experiment captures this mystery perfectly. When particles like electrons are fired toward two narrow openings, they produce an interference pattern like a wave passing through both slits simultaneously. But if you watch which slit the electron goes through, the pattern disappears. The electron behaves differently simply because you observed it. The act of measurement seems to collapse the electron's possibilities into a single outcome. But why does this collapse occur? What mechanism forces the universe to choose one path over another? Quantum mechanics gives predictions, not explanations. For decades, the standard answer was simply that measurement causes collapse, but it never said how or why. Into this uncertainty stepped an idea proposed in 1957 by physicist Hugh Everett III. What if the wave function never collapses at all? What if all outcomes happen, but we only experience one branch? This is the many worlds interpretation. According to Everett, when a quantum event with multiple possible outcomes occurs, the universe does not pick one. Instead, it splits. Each possible outcome becomes real in its own branch of the wave function. If an electron can go left or right, then in one branch it goes left, and in another it goes right. To us, it feels like a single outcome occurred because our consciousness follows only one branch. But reality, in this view, continues to evolve along every possible line. It is a radical idea, but it solves the problem of collapse elegantly. There is no collapse. There is only the unfolding of a larger structure called the universal wave function. To understand the implication of this, imagine a single atom with two possible energy states. In standard quantum mechanics, the atom begins in a superposition, a blend of both possibilities. When measured, the superposition collapses into one outcome. But in the many worlds interpretation, the measurement does not collapse anything. Instead, the measuring device, the observer, and the atom all become entangled with each possible outcome. The universe branches into two histories, one where the atom is measured in the first state, and one where it is measured in the second. This branching does not require consciousness, intelligence, or decision. It happens automatically as a consequence of how quantum systems evolve. It is silent, instantaneous, continuous. And because quantum events happen constantly, the branching is happening everywhere, all the time. If this interpretation is correct, then reality is not a line. It is a constantly expanding tree of possibilities, with each branch just as real as the one you inhabit. But the many worlds interpretation is not just metaphysical imagination. It emerges directly from the mathematics of quantum mechanics. The equations say that quantum states evolve smoothly and deterministically according to Schrödinger's equation. Collapse is not part of that equation. It must be added manually. Everett's idea was to remove the collapse postulate entirely, let the wave function evolve naturally, and accept that the universe becomes more complex as it does so. This interpretation also aligns naturally with decoherence, a phenomenon discovered decades after Everett's proposal. Decoherence describes how quantum superpositions interact with their environment. A particle in superposition is delicate. The moment it interacts with air molecules, photons, or anything else, its superposition spreads into a vast network of entangled states. These states no longer interfere with each other, making each outcome appear classical. In other words, decoherence explains why quantum branching happens, but why we only observe one outcome. Each branch becomes isolated from the others, not by walls or barriers, but by the fragility of quantum coherence. Once the branches separate, they no longer interact. They evolve independently, each becoming its own world. This idea paints an astonishing picture of reality. Every quantum event, every atomic vibration, every chemical reaction, every fluctuation in the early universe may have spawned new branches. Some branches might differ only slightly. An electron spins up instead of down. A photon reflects rather than absorbs. Others could diverge dramatically over time, leading to universes where stars form differently, galaxies evolve differently, or physical constants branch toward new outcomes. But it is important to clarify that many worlds does not describe worlds where conscious decisions create branching. It is not a theory of alternate histories in the sense of storytelling or fiction. It is a theory of quantum evolution. The branching is physical, not emotional. It occurs at the level of fundamental particles, whether humans exist or not. The unsettling part of the idea is not the existence of other branches. The unsettling part is what it implies about the nature of the self. If the universe branches with every quantum event, then there are countless versions of you, each following a different path through the expanding wave function, not copies drifting through parallel dimensions, but entanglements evolving naturally from the same initial state. Still, many worlds is not universally accepted. Some physicists argue that it introduces an infinite number of unobservable universes without providing new testable predictions. Others embrace the interpretation because it treats the mathematics of quantum mechanics with complete honesty. No collapse, no hidden variables, just the wave function evolving exactly as the equations demand. Even though we cannot observe the other branches directly, many worlds helps explain why quantum mechanics works so consistently. It removes the need for special rules or privileged observers or mysterious instantaneous collapse. In Everett's view, the universe is simply following its most fundamental laws, expanding into all possible outcomes with perfect neutrality. Yet for all its clarity, the interpretation raises profound questions. What determines how the branches separate? What is the structure of the larger wave function? How do probabilities arise if all outcomes occur? And perhaps most mysterious of all, why does our consciousness experience only one path? Some researchers believe the answer lies in decoherence. The moment a quantum system becomes entangled with its environment, each branch becomes effectively sealed off. Your awareness, tied to the particular configuration of particles in your brain, follows the branch in which those particles evolved. The other branches continue, but you have no access to them. In that sense, the branching universe is not a place for alternate selves to communicate or cross. It is a structure of possibilities that evolve without interaction. Others argue that consciousness might simply be the subjective experience of riding one branch through the wave function. You are not splintering. Reality is. Still, the idea remains one of the most thought-provoking in all of physics. If many worlds is correct, then every moment of uncertainty is not resolved. It is multiplied. Every quantum flicker, every cosmic fluctuation, every atomic shift is the birth of new histories. And our universe is just one path among a near infinite number of them. And as we drift deeper into what quantum mechanics implies, one quiet question begins to rise. If quantum branching is real, what does it mean for the structure of universes beyond our own? Part 4. Why cosmic inflation leads naturally to a multiverse. Inflation theory explains why our universe looks smooth, flat, and uniform on large scales. But the same equations that shape this smoothness also predict something surprising: that inflation should produce infinite regions of spacetime disconnected from our own. Each begins with different quantum fluctuations, leading to different physical constants. If inflation occurred as our best measurements suggest, multiple universes are not just possible, they are almost inevitable. To understand how profound this is, we need to go back to the very moment inflation was proposed. In the early 1980s, physicist Alan Guth was trying to solve a set of puzzles about the universe that seemed to defy explanation. Why is the universe so uniform? Why does space appear so flat, neither curved inward nor outward on cosmic scales? And why are distant regions of the universe so similar, despite being too far apart for light to have ever connected them? Something in the early universe had to smooth things out, flatten things out, and spread things out. Inflation was the answer, a period of rapid exponential expansion that took the newborn universe and stretched it beyond comprehension. During inflation, space itself expanded faster than the speed of light. Nothing traveled faster than light through space, but space expanded between objects at a rate that outpaced any particle, any photon, any signal. This expansion smoothed out irregularities like stretching a wrinkled fabric until it becomes taut and uniform. It also made the universe appear flat, because inflation magnified any curvature so dramatically that it became imperceptible across our observable horizon. But the more cosmologists developed this idea, the more they realized something extraordinary. Inflation does not simply solve old problems, it opens new worlds, because the physics that makes inflation smooth and powerful also makes it unpredictable on the smallest scales. The inflationary field, the energy that drove this expansion, is fundamentally quantum in nature. And quantum fields fluctuate, they ripple, jitter, and momentarily spike in energy in random, unpredictable ways. These fluctuations are tiny, but during inflation, they get stretched to cosmic scales. The places where the inflaton field dips fall out of inflation earlier. The places where the field stays high continue expanding. This creates a patchwork of regions where inflation ends at different times. Like a pan of water heating on a stove, inflation does not switch off uniformly. It bubbles. Each bubble becomes a universe. The moment inflation stops in a particular region, the energy of the inflaton field converts into particles, radiation, and eventually atoms. A Big Bang unfolds inside each bubble, but outside each bubble, inflation continues, stretching space ever further and creating room for even more bubbles to emerge. This process is called eternal inflation because it does not end everywhere simultaneously. It ends locally, pocket by pocket, bubble by bubble, while the rest of space-time continues to grow at unimaginable speed. This is why the multiverse is not a fringe idea. It is a natural consequence of how inflation behaves when combined with quantum mechanics. If inflation is true, the multiverse is not an exotic add-on. It is coded into the mathematics itself. Even more astonishing is what these bubbles inherit. Because quantum fluctuations determine when and how inflation stops in each region, they also influence the conditions inside that region. The density of matter, the rate of expansion, the balance between forces, the spectrum of fluctuations that seed galaxies. These tiny quantum differences, magnified billions of times, can lead to universes with different properties. Slight changes in the inflaton field could yield alternate versions of physical constants. A stronger electromagnetic force, a different mass for electrons, or even different numbers of spatial dimensions. Some universes might expand too quickly for galaxies to form. Others might collapse almost immediately. But in a vast cosmic landscape of possibilities, some will have conditions suitable for complexity, structure, and perhaps life. Our universe may simply be one of these successful bubbles, a region where inflation ended just right. Yet, even with this grand picture, there is something deeply quiet and humbling about inflation. The theory does not describe universes popping into existence with explosions or violence. It describes a smooth stretching of space-time, an expansion so uniform that it appears calm, even gentle. The bubbles that form are not spheres drifting in a void. They are entire space-times, expanding internally, each with its own timeline, its own matter, its own light. To an observer inside a bubble universe, like us, everything looks self-contained. We see our own cosmic microwave background. We measure our own laws of physics. We trace our own cosmic history back to its beginning. But we cannot see beyond our bubble's horizon. The boundary is not physical, it is geometric. The space between universes expands so rapidly that not even light can bridge it. This is why other universes, if they exist, remain hidden. The multiverse is not hidden behind walls or forces, it is hidden behind exponential expansion. But even though we cannot see other bubbles directly, the evidence for inflation is remarkably strong. The cosmic microwave background contains tiny fluctuations in temperature, ripples of density that inflation would naturally create. These ripples follow a statistical pattern that matches inflation's predictions with stunning precision. The large-scale structure of galaxies traces this pattern too, forming a cosmic web that grew from those early fluctuations. We also observe that the universe is extremely flat, exactly as inflation predicts. And the distribution of matter, the uniformity of the sky, and the lack of exotic relics all support the idea that some kind of inflationary expansion must have occurred. If inflation happened, then the multiverse is not a speculative leap. It is the straightforward consequence of extending inflation slightly further. The equations that explain our universe do not end neatly where our horizon begins. They continue outward. Still, scientists are cautious. The multiverse cannot be observed directly. It pushes the boundary of what physics can test. Yet paradoxically, it also helps explain why our universe looks the way it does, why its constants seem finely tuned, why galaxies formed, why stars ignited, why complexity exists at all. If there are countless universes with different properties, it is not surprising that one of them, ours, has the right conditions for life. We observe these conditions because observers can only arise in universes where those conditions exist. In this way, inflation gives us a natural explanation for the apparent fine-tuning of physics. Instead of requiring a single universe to be perfect, inflation provides a cosmic canvas with countless attempts, countless variations, countless expressions of physical law. And yet, despite all its explanatory power, inflation remains deeply mysterious. We still do not know what the inflaton field truly is or what triggered inflation to begin. We do not know what existed before it or whether before even makes sense. We do not know how many bubbles exist or whether their properties vary wildly or only subtly. But what we do know is that inflation makes a multiverse not only possible, but likely. The evidence that inflation occurred is strong. The mathematics behind eternal inflation is robust, and the logic is simple. If inflation can stop in one place, it can stop in many. And as we follow this idea deeper, one question naturally rises. If inflation created countless universes, what governs the laws within each one? Part 5. The landscape of string theory. String theory describes reality not as particles, but as vibrating strings in higher dimensions. These extra dimensions can fold, curl, or compactify in countless stable ways, each producing different physical laws. Physicists call this immense catalog of possible universes the string landscape. Our universe may simply be one stable configuration among perhaps 10,000 others. To understand why this idea even arises, we must start with a simple puzzle. The forces of nature do not want to live together. Gravity, electromagnetism, and the nuclear forces behave so differently that unifying them into a single mathematical framework has challenged physicists for almost a century. Quantum mechanics describes three of these forces with extraordinary precision. But gravity, the quiet sculptor of the cosmos, refuses to fit into that picture. At the smallest scales, our theories break down. At the Planck length, spacetime becomes turbulent and uncertain, and our equations crumble. String theory was born from the hope of repairing that fracture. Instead of treating particles as points without size, it treats them as tiny strings, loops or segments of energy vibrating in space. The vibration patterns of these strings produce what we interpret as particles. A string vibrating one way appears as an electron. Another mode of vibration appears as a photon. Yet another appears as the graviton, the hypothetical particle of gravity. In this view, the universe becomes a symphony of vibrations and matter becomes music. But this picture comes with a cost. Strings cannot vibrate consistently in just 3 dimensions of space. For the mathematics to remain stable and elegant, string theory requires additional dimensions, 6 extra in the most common versions, bringing the total to 10. These dimensions are not wide open like the ones we move through. They are compactified, curled tightly in shapes so small they evade all detection. The shape of these extra dimensions determines the laws of physics in the large dimensions we live in. This is the heart of the string landscape. Imagine the extra dimensions as a tiny origami folded into a shape so small it lies hidden in every point of space. The exact folds, twists, and connections of this microscopic geometry influence how strings can vibrate. Those vibration patterns determine particle masses, force strengths, and even the number of families of quarks and leptons. Change the geometry, and you change the universe. For a long time, physicists hoped there might be only one consistent way to fold these extra dimensions, one perfect shape that would produce the universe we see. But as mathematical techniques improved, they discovered the opposite. There were not 1 or 10 or 100 possibilities. There were at least 10 to 1,000 stable configurations, each corresponding to a different possible universe. In some of those universes, gravity might be stronger. In others, atoms might not exist. In others still, no structure might form at all. The landscape is vast, a silent catalog of possibilities, most barren, some exotic, a few perhaps hospitable. This realization changed everything. Instead of asking why our universe has the laws it does, string theory suggests a different question. Out of the enormous landscape of possible universes, why are we in this one? There is no need for a special mechanism, no need for fine-tuning or coincidence. The landscape simply contains universes with every possible combination of physical laws. Most are unremarkable. A few permit galaxies, stars, chemistry, and life. We live in one of those few, not because it was chosen, but because it is one of the stable configurations that allow observers to exist. But the landscape becomes even richer when we consider how these configurations might arise. In string theory, the early universe could have gone through processes that compactified dimensions in different ways in different regions. Quantum fluctuations, topological transitions, and energetic instabilities could all produce regions of space with distinct internal geometries. If the universe underwent enormous expansion, as inflation suggests, then countless regions could freeze into different shapes, each forming its own pocket universe with its own string compactification. The multiverse of inflation blends seamlessly with the landscape of string theory. One creates bubbles, the other fills them with different laws. This is why many cosmologists think the two frameworks, though developed separately, might be describing parts of the same tapestry. Inflation provides the stage. String theory provides the diversity. Still, we must be careful. The landscape is not a whimsical collection of imaginary universes. It is a mathematical space defined by specific equations, constraints, and symmetries. Each point in the landscape corresponds to a particular way the extra dimensions can be shaped. Some shapes are smooth, others jagged. Some resemble six-dimensional analogs of spheres, tori, or complex manifolds. Others are intricate beyond visualization, woven through with tunnels, holes, and twists that have no analogy in our familiar world. These shapes, known as Calabi-Yau manifolds, are objects of pure geometry, yet they carry the seeds of physics. Every Calabi-Yau shape produces a different spectrum of particles, a different arrangement of forces, a different vacuum energy. In some, the vacuum energy is positive, leading to universes that expand rapidly. In others, it is negative, causing universes to collapse quickly. Somewhere in that vast space lies the combination that produces the physics we observe: electrons with their specific mass, neutrinos with their ghostly lightness, and photons that travel at the speed they do. Our universe might simply be one of those points. But string theorists also discovered something else. The landscape is not static. It is riddled with transitions, pathways by which one vacuum state might tunnel into another. Under the right conditions, a universe could undergo a quantum transition, flipping the shape of its extra dimensions. If such a transition happened in our universe, it would be catastrophic, reshaping every law of physics instantly. But in the vast multiverse, such transitions might happen constantly in distant regions, carving out new bubble universes with new properties. This dynamic picture suggests that the multiverse is not just a set of separate universes, but a living landscape through which spacetime continuously evolves. Some regions stabilize, some decay, some give rise to new universes, and the process never ends. Yet, for all its complexity, there is something profoundly quiet about the landscape. It is not noisy, it is not chaotic. It is a mathematical structure, silent and still, like a library of possible realities written in the language of higher dimensional geometry. We exist in one chapter, a chapter shaped billions of years ago when the universe cooled enough for the extra dimensions to settle into their present form. And even though the landscape is unimaginably vast, it raises one deeply grounding thought. The laws of physics we experience are not the only ones possible. They are simply the ones that arose here. The string landscape does not diminish the beauty of our universe. On the contrary, it expands it. It suggests that the cosmos is far more intricate than our senses can know, that the constants we measure are not universal truths, but local expressions of deeper geometric patterns. And as we drift deeper into this mathematical multiverse, one question begins to settle softly. If our universe is just one configuration among countless others, what determines which universes can give rise to complexity, structure, and life? Part 6. Why the fine-tuning of physics raises big questions. Many constants in nature, the strength of gravity, the mass of the electron, the balance between forces, appear finely tuned for stars, chemistry, and life. If they were slightly different, galaxies might never form. In a multiverse, fine-tuning is not a mystery but a statistical outcome. Out of countless universes with random physical parameters, only a few would allow complex structures to emerge, and we happen to inhabit one of them. When scientists talk about fine-tuning, they are not suggesting intention or design. They are simply noticing something quietly remarkable. The universe's physical numbers sit in a very narrow range. Adjust them even a little, and the universe we know would fall apart long before anything resembling life had a chance to form. And yet, here we are, living in a cosmos where these constants align in just the right way for stars to ignite, planets to form, and chemistry to flourish. Gravity is a perfect example. It is incredibly weak compared to other forces, weaker by a factor of 1038 than electromagnetism. If gravity were even slightly stronger, stars would burn too quickly and collapse into black holes before heavier elements could form. If it were weaker, matter would drift apart and stars might never fully ignite. Our universe sits precisely on the narrow ridge where stellar furnaces can operate for billions of years, long enough to forge the carbon and oxygen needed for biology. The mass of the electron is another delicate number. If electrons were significantly heavier, atoms would be unstable or would not form the complex chemical structures necessary for life. If they were lighter, chemical bonds might be too weak to support stable molecules. Yet the electron's mass arrives in a narrow band that allows both atoms and chemistry to exist. Even the balance between the nuclear forces is finely tuned. The strong nuclear force binds protons and neutrons in atomic nuclei. If this force were just a few percent weaker, hydrogen would be the only stable element. If it were a few percent stronger, almost all hydrogen would fuse too early into heavier elements, and stars like ours would never ignite. The delicate balance between hydrogen and heavier elements is essential for water, organic molecules, and energy-producing stars. When you begin listing these coincidences, a quiet pattern emerges. Everywhere you look, from cosmology to particle physics, the universe appears delicately arranged to permit complexity. It is not that everything is perfectly balanced, it is that the balance exists at all. This raises a profound question. Why? Why do the constants of nature fall within the narrow window that allows the universe to evolve as it did? In a single universe framework, the fine-tuning looks improbable, but in the multiverse framework, it becomes almost inevitable. If there are countless universes with different physical constants, then the rare ones that permit complexity will also be the only ones where observers can arise to ask these questions. This idea is sometimes called the anthropic principle, though the term is often misunderstood. It does not claim that the universe was made for observers. It simply acknowledges a quiet truth. Observers can only exist in universes that allow observers. It is not a statement about purpose, it is a statement about selection. In this sense, the fine-tuning of physics may be evidence for the multiverse. Not direct evidence, but indirect, a whisper rather than a measurement. If the landscape of possible universes is vast, then some will naturally fall within the narrow window that permits complex chemistry, long-lived stars, and stable matter. And one of those universes might be ours. But the fine-tuning question becomes even more striking when we examine the cosmological constant, the energy of empty space. Observations show that it has a tiny positive value, causing the universe to expand at an accelerating rate. If the cosmological constant were much larger, galaxies could never form. If it were negative, the universe would collapse quickly. Its observed value is so improbably small, around 10^120 in natural units, that some physicists consider it the single most finely tuned number in all of physics. In a single universe model, this seems inexplicable, but in a multiverse, where the vacuum energy varies from universe to universe, only universes with a small cosmological constant would allow galaxies to form, and only in those universes would observers ever arise. Still, the fine-tuning problem is not just about numbers. It is also about the structure of physical laws. Certain equations only work because parameters sit exactly where they need to be. Certain symmetries appear stable only because of delicate cancellations. Even the fact that the universe cools at the right pace to allow complex structures is not guaranteed. It emerges from a careful interplay between expansion, matter density, and radiation. Nothing about this balancing act seems arbitrary, but at the same time, nothing requires it. The multiverse provides a natural explanation. In a vast space of possibilities, we inhabit one of the rare stable configurations. Yet, for all its explanatory power, some physicists remain cautious. They worry that the multiverse, while elegant mathematically, may not be testable. They prefer explanations rooted in deeper physical principles that may one day show why the constants had to be the way they are. Perhaps there is a deeper theory, still hidden, that locks these values into place. Others argue that fine-tuning itself hints that we are looking at the problem from the wrong angle. Maybe the constants appear fine-tuned not because the universe was configured to allow complexity, but because complexity is only possible where the constants take those values. In other words, we see the universe as tuned because our existence filters what we can observe. This is not mysticism, it is simple probability. Still, fine-tuning can be unsettling. It leaves us with a sense of fragility, the idea that our universe rests on a knife edge. Yet there is another way to see it. If the multiverse is real, then the fragility we perceive is simply the rarity of our viewpoint. Most universes might be barren, sterile, or short-lived, but that does not diminish the one universe where complexity arose. Instead, it highlights its uniqueness, and that uniqueness carries quiet beauty. The laws that govern the fusion in our sun, the chemistry that shapes your body, the stability of water, the existence of carbon, all emerge from a set of physical constants that fall into the narrowest window we know. They allow stars to breathe for billions of years. They allow planets to cool and form atmospheres. They allow molecules to bind in ways that build memory, movement, and life. If the multiverse exists, we are part of the rare fraction where matter learns to think. Still, even the multiverse does not answer everything. It shifts the question, but it does not eliminate it. Why does the multiverse exist? Why do the underlying laws allow such variation? Why does the cosmic landscape contain the configurations it does? Physics has not yet answered these questions, but the fine-tuning problem ensures that we keep asking them. It forces us to consider deeper possibilities, that the universe is not the only universe, and that our place within it is shaped by a quiet interplay of chance and necessity. And as we drift into the next chapter, one question gently follows. If our universe is one of the rare few that allow complexity, what does that say about the universes that do not? Part 7. Are black holes gateways to new universes? Some theoretical models suggest that the singularity at a black hole's center might not be an end but a beginning. Under extreme compression, spacetime could curve into a new expanding region, a daughter universe branching from a parent. If so, every black hole could be a seed of cosmic rebirth, creating universes with slightly altered physical laws. To explore this idea, we must first understand what makes black holes so strange. In the familiar world, gravity pulls things toward the center of mass. But in a black hole, gravity becomes so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. Inside this boundary, all paths lead inward. Space curves so steeply that motion has only one direction, toward the singularity, a point where density and curvature become effectively infinite. At least, that is how classical general relativity describes it. But this description is incomplete. At the singularity, the equations of general relativity break down. They predict infinite density, infinite curvature, signs not of physical reality, but of a theory reaching its limits. Something deeper must happen at the center of a black hole, and in that uncertainty, new possibilities arise. One such possibility is that the singularity is not a point of destruction, but a transition, a doorway, a place where space-time pinches off from our universe and opens into another, creating a new, expanding region with its own timeline, its own laws, and its own cosmic horizon. This idea is known as the black hole cosmology hypothesis, and while it remains speculative, it sits at the intersection of several powerful theories: general relativity, quantum gravity, and cosmology. To see how it works, imagine space as a fabric. A black hole forms when enough mass compresses a region of this fabric so tightly that it creates a deep funnel. At the bottom of that funnel, instead of a hard endpoint, the fabric might twist into a new sheet of spacetime, a separate universe inflated away from our own. From the viewpoint of that new universe, the moment of its birth might look like a big bang, a sudden expansion from a tiny, dense state. In this model, black holes become cosmic wombs. Every time a star collapses into a black hole, the extreme conditions at its core could ignite a new universe. If this is true, our universe might itself have begun inside a black hole within some parent universe, its big bang the moment it emerged from the singularity of another cosmos. This sounds fantastical, but it arises naturally in the mathematics of spacetime. General relativity allows spacetime to curve and stretch in ways that can connect one region to another through structures called Einstein-Rosen bridges. These bridges, often called wormholes, are typically unstable, collapsing too quickly to permit travel. But inside a black hole, the geometry is more nuanced. Instead of forming a symmetrical wormhole, the collapse may create a one-way bridge, a passage from a parent universe into a new, expanding child universe. From the outside, the black hole looks like an end, a place where matter disappears forever. But from the inside of the new universe, the singularity looks like the beginning, the first moment of time. This picture aligns with a broader idea in theoretical physics, that universes may form in cycles or chains, each being born from the death of stars in previous universes. Some physicists call this cosmological natural selection. The idea is simple but profound. Universes that produce many black holes give rise to many daughter universes. Those daughter universes that happen to have physical laws conducive to black hole formation become more common in the multiverse. Over immense cosmic generations, universes may evolve toward laws that maximize black hole production. If this is true, then the fine-tuning of our universe, the delicate balance that allows stars to form, galaxies to grow, and black holes to arise, may not be a coincidence. It may be the result of cosmic heredity. Our universe's laws may have been selected because they allow the creation of black holes, which in turn give rise to new universes. Yet even if we set aside these evolutionary ideas, the basic concept still stands. Inside a black hole, space-time may not end, it may transform. But what would it feel like for matter falling into such a region? From the outside, matter appears to slow as it approaches the event horizon, fading into darkness as time stretches. But from the perspective of the matter itself, it falls inward without hesitation, crossing the horizon in a finite time. Once inside, space curves relentlessly. The future of everything is the singularity. Whether the matter is destroyed or reborn depends on the true nature of that singularity, a nature we still do not fully understand. Quantum gravity, a theory not yet complete, might smooth out the singularity, replacing it with a region of extreme but finite density. If so, this region could bounce, creating a new expanding spacetime. Some models call this a bounce cosmology, in which collapse in one universe becomes expansion in another. In these models, the equations of general relativity are modified by quantum effects. When matter reaches a critical density, the collapse reverses. Instead of infinite compression, spacetime rebounds. To the new universe, this rebound looks like a big bang. To the parent universe, it looks like a black hole. This means our own universe could carry the imprint of a bounce, subtle hints in the distribution of matter or the pattern of cosmic fluctuations. The cosmic microwave background has been studied intensely for such signatures, though none have been confirmed. The idea remains speculative, but not impossible. Another compelling aspect of the black hole universe connection is that it explains the problem of information. According to quantum mechanics, information cannot be destroyed. But black holes seem to destroy information by swallowing matter and evaporating via Hawking radiation. If instead the information escapes into a new universe, carried by the branching geometry of spacetime, then nothing is lost. It is simply transported elsewhere. This idea remains controversial, but it offers a path toward reconciling quantum mechanics with gravity. Still, we must acknowledge the limits of our understanding. No probe can cross the event horizon and return. No telescope can peer into the heart of a singularity. Everything we infer is built from mathematics, symmetry, and the belief that physical laws remain consistent even under extreme conditions. Black holes are the most extreme objects in the universe, and they sit at the boundary of what we know and what we hope to know. Yet their potential role in cosmic creation is philosophically beautiful. In a universe filled with cycles of birth and death, black holes would become not tombs but seeds, places where the fabric of spacetime folds inward only to bloom outward elsewhere. Imagine the stars we see tonight, each one bright, ancient, burning through its nuclear fuel. Many of them will end as black holes. Some already have. If the black hole cosmology idea is correct, then the universe is filled with silent gateways, each with the potential to open into something new. And somewhere in that chain of cosmic birth, perhaps our own universe took shape, emerging from the death of a star in a parent universe we will never see. In this quiet vision, nothing is ever truly lost. Everything transforms, everything continues. And as we drift into the next question, one gentle thought rises. If black holes give birth to universes, could the properties of our universe reflect the conditions of the one that came before? Part 8. The quiet clues hidden in the cosmic microwave background. The cosmic microwave background, the faint afterglow of the Big Bang, is our oldest light. Some cosmologists search it for subtle asymmetries, cold spots, or circular patterns that might hint at collisions between our universe and others. These signatures, if ever confirmed, would be the first physical trace of a multiverse brushing against our own. When you look at the night sky, you see stars thousands of light years away. When you look deeper with a telescope, you see galaxies millions or billions of light years distant. But the cosmic microwave background, the CMB, is something far more ancient. It is not starlight. It is not galaxy light. It is the leftover radiation from when the universe was only 380,000 years old, a time when atoms first formed and light could finally travel freely. Before that moment, the cosmos was opaque, filled with a hot plasma that scattered photons endlessly. When the universe cooled enough for electrons to bind to nuclei, the fog lifted and light escaped, a soft glow that has been traveling through space for nearly 14 billion years. That glow now fills the universe as a gentle microwave background. It is almost perfectly uniform. Its temperature is nearly the same in every direction, only slightly above absolute zero. And yet those tiny temperature differences, only a few millionths of a degree, are the fingerprints of our earliest cosmic history. They reveal how matter was distributed, how galaxies would later form, and how the seeds of structure were planted. The CMB is a cosmic fossil, but it may be more than history. It may carry quiet hints of worlds beyond our own. If other universes exist, and if they ever came close enough to ours, their presence might leave scars. Not dramatic ones, not vivid lines or glowing patterns, but delicate imprints in this ancient light, subtle distortions, slight asymmetries, shadows that do not belong to any known physical process. Cosmologists have spent years searching for these clues. One of the most intriguing possibilities comes from bubble collisions predicted by eternal inflation. If inflation produced many bubble universes expanding in a vast inflating background, then occasionally, two bubbles might drift close enough to touch. Such a collision would not merge the universes. Spacetime itself would separate them too strongly, but it could produce a disturbance, a circular imprint formed when the edges of the two expanding bubbles grazed each other. This is what researchers look for: circular features in the CMB that cannot be explained by normal cosmic evolution. Some studies have reported possible circles, others find nothing meaningful. The debate remains open, quiet, but persistent. The CMB is noisy, not in sound, but in statistics. Random patterns can mimic real ones. Separating signal from noise requires immense care. Another quiet anomaly is the CMB cold spot, a region hundreds of millions of light-years wide where the temperature is slightly lower than expected. In a universe governed only by standard physics, such a cold spot is statistically unlikely. Some propose it formed from a massive void, an unusually large region lacking galaxies, bending the CMB photons through gravitational lensing. Others suggest it may be evidence of a bubble collision, a bruise left by an interaction with another universe long ago. If the cold spot is a birthmark of the multiverse, it would be the first tangible sign that our cosmic bubble once encountered another. And yet, the evidence is far from conclusive. The cold spot could be a statistical fluke. The circles might be illusions produced by random noise. The asymmetries could arise from subtle imperfections in our instruments. The CMB demands humility. It whispers clues, never shouts them. Still, the fact that cosmologists even know what to look for is remarkable. Inflationary models predict specific patterns, temperature rings, aligned anomalies, shifts in polarization. If two universes interacted, physics suggests the collision would leave a boundary across the sky, a place where the density of the early universe changed abruptly. Such a collision might produce a disc-shaped region, a faint but measurable trace. The search continues not because scientists expect a dramatic revelation, but because even the smallest deviation could reshape our understanding of reality. Another mysterious feature of the CMB is something called the axis of asymmetry, or the axis of evil. It refers to the observation that the large-scale patterns in the CMB appear to align along a particular direction in the sky, rather than being completely random. In standard cosmology, no direction should be special. The universe should look the same on large scales in every direction. But this alignment has persisted across multiple experiments, including WMAP and Planck. Most physicists suspect a mundane explanation, statistical noise or foreground interference, but a few have wondered whether it could be a sign that our universe has a preferred direction, perhaps inherited from physics beyond our bubble. If our universe collided with another, if some primordial structure influenced spacetime, or if inflation had a subtle directional tilt, the CMB could carry the memory. These ideas remain speculative, but they are not dismissed. The CMB is the most precise window we have into the early universe, and it contains more data than any human could comprehend at once. Algorithms search its maps for anomalies. Supercomputers simulate millions of universes to compare with our own. And still, the question remains open. Have we already seen the multiverse without recognizing it? Another line of investigation looks at polarization patterns in the CMB. These patterns, swirls called B-modes, can arise from gravitational waves in the early universe. Some models of inflation predict that bubble collisions would create gravitational wave signatures that could subtly twist the polarization of the CMB. Detecting these patterns would not prove the multiverse, but it would offer a tantalizing step, evidence of processes beyond the standard cosmological model. The Planck satellite has already mapped the CMB's polarization with exquisite detail. More sensitive missions are planned. The hope is that buried in the soft glow of ancient light, we might find a whisper of something more, a hint that our universe is just one part of a larger cosmic structure. Yet for all the speculation, the CMB remains fundamentally serene. Its near-perfect uniformity is not a sign of emptiness, but of deep cosmic harmony. The universe began with extraordinary smoothness, and that smoothness has allowed galaxies, stars, and worlds to unfold over billions of years. The CMB is a reminder that even small fluctuations can grow into entire cosmic structures, and perhaps in its most delicate variations, it hides the faint echoes of other universes. The search for clues in the CMB is not driven by a desire for sensational discovery. It is driven by curiosity, the quiet, patient curiosity that defines science at its best. We explore not to confirm our expectations, but to test them, to see whether the universe contains surprises we have not yet imagined. If the multiverse touched ours, the CMB might be the only place we could ever detect it, not through bright signals, but through faint shadows, not through definitive proof, but through patterns that refuse to fit neatly into our existing models. Whether those clues ever emerge clearly, the cosmic microwave background will remain our oldest map, a soft, ancient glow that holds the memory of everything the universe once was. And as we move deeper into the multiverse idea, one question rises gently from this primordial light. If the CMB carries faint hints of other universes, what prevents us from seeing beyond our own cosmic horizon? Part 9. Why we can't see beyond our cosmic horizon. Light travels at a finite speed, and the universe has been expanding for 13.8 billion years. That means we can only see a limited region of space, a cosmic bubble around us. Beyond this horizon, countless regions may exist, each unreachable and unobservable. The inability to see them is not evidence they do not exist. It is a consequence of the finite speed of light and the expansion of spacetime. To understand why this horizon exists, imagine sitting by a calm lake at dawn. The water stretches outward, reflecting the faint sky. You see far, but not infinitely. Beyond a certain distance, the earth curves away, hiding what lies further. The horizon does not mean the world ends there. It simply marks the limit of what light can reach your eyes. Our universe behaves the same way, but on a scale so vast, it defies comprehension. When we look into space, we are also looking back in time. Light from the nearest star took 4 years to arrive. Light from distant galaxies took hundreds of millions. The cosmic microwave background, the faint afterglow of the Big Bang, took nearly 14 billion years to reach us. Beyond that, even older light simply has not had time to arrive. The universe is not infinitely old, it had a beginning. And because light travels at a finite speed, there is a limit to how much of the universe we can ever observe. This boundary is called the cosmic horizon. Everything we can possibly see with any telescope belongs to the observable universe, a bubble around us roughly 93 billion light-years across. That number may seem paradoxically large. How can the observable universe be 93 billion light-years wide if the universe is only 13.8 billion years old? The answer lies in the expansion of space itself. As light travels through the cosmos, the fabric of space stretches beneath it. Galaxies are carried away from one another, not because they are moving through space, but because space is expanding between them. This expansion has been occurring since the Big Bang, pulling distant regions farther away, even as their light journeys toward us. By the time that ancient light arrives, the space it traversed has grown enormously. This is why the observable universe is larger than 13.8 billion light years. It is the result of space stretching during the entire journey of that light. But beyond this observable region, space continues. It does not end at the horizon. It is simply unobservable, forever outside our view. Not because of obstacles or distance, but because no signal, not even one traveling at the speed of light, can ever bridge the growing gap. This leads to a quiet but profound realization. Our universe may be vastly larger than the part we can see, possibly infinite, and we are confined to a small piece of it, not by technology, but by the laws of physics. The cosmic horizon is not a physical barrier. There is no wall, no boundary, no edge. There is only the geometry of time and light, limiting how far the past can reach us. To visualize this, picture blowing a soap bubble. You stand on its surface, unable to see the far side, not because you are blind, but because the bubble curves in such a way that sight lines are limited. Now imagine that the bubble is expanding. As it grows, more of the surface becomes unreachable. No matter how your eyes strain, you are confined to a shrinking fraction of the whole. This is our position in the cosmos. We stand inside an expanding sphere of visibility, one defined not by where the universe ends, but by how far light has traveled since the beginning of time. And because the expansion of the universe is accelerating, driven by dark energy, some regions that were once drifting toward visibility are now receding faster than light can ever compensate. Their light will never reach us, not even in eternity. They are being carried away so swiftly that the distance between us and them grows faster than any photon can cross. This means the observable universe is shrinking in a subtle conceptual way, not in size, but in accessibility. Every year, more galaxies slip beyond the horizon. They still exist. They are simply gone from view forever. This creates a twofold horizon, a past horizon, limiting how much of the early universe we can see, and a future horizon, limiting how much of the current universe we will ever see. Beyond those horizons lies an expanse of space we can never access. But this does not imply emptiness. It implies hiddenness. The universe does not care what we can observe. It continues expanding everywhere, whether or not its distant regions lie within our cosmic bubble. The multiverse hypothesis leans heavily on this idea, that what lies beyond the horizon may include other regions formed with different initial conditions, different physical constants, or even entirely separate inflationary bubbles. Our inability to observe them is not a sign they do not exist. It is a sign that spacetime itself protects their isolation. Some cosmologists compare the cosmic horizon to the horizon of a black hole. In a black hole, the event horizon marks the point beyond which no information can escape. In the universe, the cosmic horizon marks the point beyond which no information can reach us, not because of extreme gravity, but because expansion outpaces communication. The effect is the same, a limit on what can ever be known. And yet our horizon is not fixed. As time passes, we see farther back. Every year that passes, we observe slightly older light from slightly more distant regions. But even as our past horizon expands, our future horizon contracts. The universe grows larger, galaxies drift away, and beyond a certain distance, light can no longer keep up. In this way, the universe gently closes behind us even as it opens before us. This has important implications for the multiverse. If inflation produced many bubble universes, each would be separated by regions of space that expand faster than light can cross. No causal contact is possible between bubbles. Our cosmic horizon is simply the local horizon of our bubble. And just as a ship on Earth sees only the ocean around it, unaware of continents beyond the horizon, we see only our local region of the multiverse. Everything beyond remains invisible, but not necessarily non-existent. The cosmic horizon also shapes how we interpret cosmological evidence. Because we can only see a finite patch of the universe, we cannot know for certain whether the universe as a whole is flat or curved, finite or infinite. Our measurements suggest flatness, but that conclusion applies only to the portion we can observe. Beyond that region, space may curve differently. Matter may clump differently. The distribution of galaxies may shift. The physics may subtly change. We cannot know. And not because we lack instruments, but because we lack access. This limitation is not a flaw. It is a fundamental feature of living in a universe that has a beginning, an expansion, and a finite speed of light. It is the cosmic equivalent of trying to read a book while only seeing the pages illuminated by a candle. Still, there is something beautiful about these limits. They remind us that the cosmos is larger than our perception. They remind us that mystery is not an obstacle, but an invitation. They remind us that the universe extends beyond the reach of thought and that the multiverse, if it exists, might forever remain a horizon beyond our horizon. And as we drift deeper into this quiet frontier, one soft question begins to rise. If we can never see beyond our cosmic horizon, how can we tell whether other universes might have different laws of nature? Part 10. Could other universes have different physics? If multiple universes exist, some could have stronger gravity, faster cosmic expansion, or entirely different particle structures. Stars might never ignite, atoms might never form, or new forms of complexity might emerge beyond anything we can picture. The multiverse is not simply a repetition. It is a landscape of possibilities shaped by different fundamental constants. To understand why physics might vary across universes, we must first appreciate how delicately our own universe is balanced. The laws we experience, gravity, electromagnetism, the nuclear forces, the behavior of particles, all arise from a set of constants that appear fixed and universal. But nothing in physics demands that those constants take the values they do. They are not the inevitable outcome of an ancient equation. They are parameters chosen by the conditions of our universe's birth. When we imagine other universes, we imagine different choices, different starting points for nature. Consider gravity. In our universe, gravity is extraordinarily weak. It is 1038 times weaker than electromagnetism. This weakness is not an afterthought. It is the reason stars burn steadily rather than explode violently or collapse instantly. If gravity were only a little stronger, stars would fuse their fuel too quickly. If it were weaker, gas clouds might never collapse into stars at all. Change gravity's strength, and the entire cosmic script transforms. In another universe, stars might be short-lived giants, or they might never form, leaving a cosmos filled only with diffuse gas, silent, cold, structureless. Now, consider electromagnetism, the force that holds atoms together. In our universe, electrons orbit nuclei because the electromagnetic force has the strength it does. But if electromagnetism were slightly weaker, atoms would be unstable, electrons would drift away, chemistry would dissolve. If it were stronger, electrons would cling too tightly to nuclei, preventing complex molecules from forming. Life as we know it depends on a narrow range between these extremes. Now, imagine a universe where the electromagnetic force is twice as strong or half as strong. In such a universe, chemistry might be unrecognizable. Perhaps complexity would arise in ways we cannot predict, or perhaps no structure would survive at all. The strong nuclear force is even more sensitive. It binds protons and neutrons inside atomic nuclei. If it were slightly weaker, hydrogen might be the only element that exists. No helium, no carbon, no oxygen. If it were slightly stronger, all hydrogen would have fused into heavier elements in the first moments after the Big Bang, leaving no fuel for stars. Adjust the strong force, and the periodic table collapses. The rules of physics are not arbitrary, but their values are not predetermined. They emerge from conditions that may vary across universes. Even the masses of fundamental particles, like the electron or the up quark, dictate the structure of reality. If the electron were heavier, atoms would be smaller and denser. If it were lighter, atoms would be diffuse and fragile. The up quark and down quark masses determine the stability of protons and neutrons. Alter them, and atoms might never form, or matter might collapse into exotic states with no parallel in our world. In our universe, these masses are tuned to extraordinary precision, allowing stable matter to exist at all. But in the multiverse, each universe could begin with different values. Some might form elegant structures unlike anything we know. Some might remain simple and barren, some might exist for fractions of a second before collapsing, and some might evolve new forms of complexity, driven by different interactions, different symmetries, or different architectures of matter. The physics we see is one configuration among countless others, but the differences may go beyond constants. They could extend into the fundamental laws themselves. Imagine a universe with more spatial dimensions. String theory suggests that spacetime might have 10 or 11 dimensions, but only 3 are extended in our universe. The rest are compactified, curled up too tightly for us to observe. In another universe, different dimensions might unfurl. Gravity might spread across more directions, weakening or strengthening in unfamiliar ways. Particles might move along paths forbidden in our cosmos. The geometry of space itself would shape the evolution of matter. Or consider the symmetries that govern particle interactions. Our universe has a specific symmetry structure described by the Standard Model. But symmetry breaking, the process by which these patterns form, could unfold differently in another universe, producing alternate families of particles, alternate types of forces, alternate mathematical frameworks for reality. If the Higgs field, responsible for giving particles their mass, had a different value, the masses of particles might shift dramatically. Some might become too heavy to exist, others might dominate the universe. The balance of matter could tilt in directions that produce exotic forms of atoms, unfamiliar forms of chemistry, or none at all. Even the nature of dark energy could vary. In our universe, dark energy causes accelerated expansion, but if its value were significantly larger, the universe would expand so quickly that gravity would never gather matter into stars. If the value were negative, the universe might collapse within minutes of its birth. Another universe could have dark energy that fluctuates, or dark energy that behaves like a field rather than a constant, or no dark energy at all. Each possibility produces a cosmos with different destinies, but the question that lingers quietly beneath these differences is whether life or complexity could exist in universes very different from our own. Most universes in the multiverse might be sterile, but some might harbor structures we cannot begin to imagine. Perhaps complexity does not require atoms. Perhaps stability could arise in networks of energy patterns or in structures built from exotic particles. Perhaps universes with different forces would produce new forms of emergence unrelated to chemistry but equivalent in subtlety. In a cosmos of endless variation, there may be many paths to complexity, not just the one we know. Yet, even if complexity is rare, rarity becomes inevitable in a multiverse. Our universe's suitability for life is not a miracle. It is a location within a vast landscape. We observe a universe compatible with life, because only in universes compatible with life can observers arise at all. In this way, the question shifts from why our universe allows life to how many universes do not. Still, the idea remains profoundly humbling. Physics is not a fixed inevitability. It is a branching of possibilities. Our universe is one expression of laws and constants. Another universe might glow with stars made from different particles. Another might be forever dark. Another might be filled with forms of matter that interact through forces we cannot visualize. Another might last only a moment before fading back into silence. Each universe carries its own script, its own beginning and end, its own internal coherence. And yet, even with all these differences, one thing remains the same across the multiverse: the quiet elegance of physical law. Whether gravity is strong or weak, whether particles are light or heavy, whether dimensions are few or many, the cosmos evolves through patterns, patterns of symmetry, energy, geometry, and time. And as we drift deeper into the vast possibility space of physics, one gentle question begins to rise. If different universes follow different laws, how might complexity itself arise in forms we cannot yet imagine? Part 11. How quantum fields could create universes from nothing. Quantum fields never sit perfectly still. They fluctuate with a tiny, irreducible energy. In extreme conditions, such as the early universe or inside regions of intense curvature, these fluctuations can give rise to new pockets of spacetime. According to some models, universes can spontaneously form from the vacuum, emerging from quantum instability rather than classical creation. To understand how something as immense as a universe could arise from nothing, we must first understand what nothing means in physics. In everyday language, nothing suggests emptiness, a void without matter, without energy, without space or time. But in quantum physics, the vacuum is never truly empty. It is a restless sea of fields, vibrating with irreducible fluctuations. Even when no particles exist, the fields themselves continue to shimmer with uncertainty. This restless vacuum is called the quantum vacuum, and it is the foundation of modern physics. Every point in space is filled with it. Every atom, every region between stars, every patch of intergalactic darkness is saturated with these fields. They cannot be eliminated. They cannot be silenced. Even at absolute zero, the lowest temperature nature allows, the fields still fluctuate with a faint hum of energy called zero-point energy. These fluctuations are not hypothetical. They have observable consequences. They allow particles to momentarily appear and disappear. They create measurable forces between uncharged metal plates in the Casimir effect. They influence the behavior of electrons in atoms. They are woven into the structure of reality. This means that the vacuum is not a passive emptiness. It is an active, dynamic medium, a canvas that can, under the right conditions, become unstable and produce new regions of spacetime. This idea lies at the heart of quantum cosmology. According to some models, our universe could have emerged from such instability, not from a pre-existing space, not from a rupture in a parent cosmos, but from the quantum vacuum itself undergoing a rare and powerful fluctuation. To see how this could work, we must examine the relationship between energy and curvature. In general relativity, energy bends spacetime. A particle changes the curvature around it. A star warps the region it occupies. A black hole distorts spacetime so drastically that its curvature becomes infinite at the singularity. But in quantum cosmology, the vacuum itself has energy, and therefore, the vacuum itself can curve. If the energy of the vacuum in a particular region spikes sufficiently due to a quantum fluctuation, that region could become gravitationally unstable. Instead of collapsing, the region might inflate, expanding rapidly into a new bubble of spacetime. Inside that bubble, the geometry could detach from the surrounding space, forming its own universe with its own timeline. From the outside, if outside is even a meaningful concept, such a universe would be too small and too isolated to detect. But from within, the bubble would expand, cool, and evolve just as ours did. To its inhabitants, the bubble would appear to be everything. One way to visualize this is to imagine a sheet of rubber representing the vacuum. Tiny ripples appear spontaneously across its surface. Most of these ripples fade quickly, but occasionally one grows large enough to distort the sheet into a dome. If the dome expands rapidly, it stretches until it pinches off from the original sheet, becoming a bubble of its own. That bubble is a universe. In the language of quantum cosmology, this process is called tunneling from nothing or vacuum decay. It is a transition from one state of the vacuum to another, from a false vacuum to a true vacuum, or vice versa. In some scenarios, the vacuum has multiple energy levels. Our universe resides in one. A quantum fluctuation could push a region into a different level, triggering the formation of a new spacetime with different physical laws. This process is not mystical. It is the application of quantum mechanics to gravity. Just as particles can tunnel through barriers they should not be able to cross, the universe as a whole can tunnel into existence. Some models, such as those developed by physicists Alexander Vilenkin and Andrei Linde, propose that the universe began in precisely this way, not from previous matter, but from quantum potential. In Vilenkin's model, the universe is the ultimate free lunch. The positive energy of matter is balanced by the negative energy of gravity, allowing the total energy to be zero. A zero-energy universe can arise spontaneously from the vacuum because it does not violate conservation laws. In this picture, nothing is not an absolute void. It is the state of lowest possible energy, and even that state contains the possibility of fluctuation. But this raises a deeper question. If universes can be created from quantum fluctuations, why do they not appear everywhere, constantly? Why is the creation of a universe so rare? The answer lies in the scale of the fluctuation required. While small fluctuations occur constantly, the creation of an entire universe demands an enormous spike in energy concentrated in a tiny region. Such fluctuations are unimaginably unlikely. The probability is not zero, but it is incredibly small. Yet given infinite time or an infinite expanse of vacuum, even rare events become inevitable. This leads to the idea of the quantum multiverse, an endless sea of universes emerging from vacuum fluctuations. Some may be tiny and short-lived, others may grow large and complex. Ours is simply one that succeeded. Quantum cosmology also suggests something profound about the Big Bang. The Big Bang was not the explosion of matter into space. It was the creation of space itself. If our universe emerged from a quantum fluctuation, then time itself may have begun in that moment. There was no before in the classical sense. There was only a transition from a quantum vacuum to an expanding spacetime, a shift in the structure of possibility. This idea challenges our intuition about creation. We imagine beginnings requiring causes. But in quantum mechanics, uncaused events are not impossible. They are part of the fabric of reality. Radioactive decay has no trigger. Particle-antiparticle pairs appear spontaneously. The vacuum hums with activity that has no classical explanation. If entire universes can arise from such processes, the multiverse becomes not a metaphysical speculation, but a consequence of quantum law. Still, we must approach this idea with humility. We cannot observe the birth of universes. We cannot probe the vacuum at the energies required for such fluctuations. Our theories remain incomplete. Quantum gravity, the unification of general relativity and quantum mechanics, is still a work in progress. Yet the mathematics points toward a quiet, elegant possibility that reality may be generative, that the vacuum may be fertile, that creation may be woven into the quantum fabric itself. In this vision, universes are not isolated miracles. They are natural expressions of the vacuum's restless nature. Each universe begins as a fluctuation, expands through inflation, and cools into its own version of physics. No two are exactly alike. Some decay quickly, others grow for billions of years. Some remain simple, others give rise to complexity and consciousness. Our universe is one such expression, a bubble of space-time sustained by quantum fields, shaped by initial fluctuations and governed by laws that emerged from its earliest moments. And as we drift into the next chapter of this cosmic story, one question rises gently. If quantum fields can create universes from nothing, what does that say about the nature of the vacuum itself? Part 12. Are we living in a simulation? Inside a larger reality? Some researchers argue that if advanced civilizations can simulate universes, it may be statistically likely we live inside one. This idea is not presented as a conspiracy, but as a question of computational physics and probabilities. If reality is emergent from deeper computational rules, then our universe may be one of many simulated realities in a nested hierarchy. The simulation hypothesis is often misunderstood. It is not about secret rooms or puppeteers behind the scenes. It is not about glitching skies or coded messages hiding in shadows. Instead, it is an exploration of an ancient question, one that physics now has the tools to consider seriously. What is the fundamental fabric of reality? Is it continuous, smooth, and infinitely divisible? Or is it discrete, quantized, and computational at its core? When physicists examine the universe at its smallest scales, they find something remarkable. Space is not infinitely smooth. Time is not infinitely divisible. At the Planck scale, reality becomes grainy, like pixels in an image or frames in a film. The foundations of spacetime behave less like a continuous sheet and more like a network of relationships, a grid of interactions. This has led some researchers to ask whether the universe might behave like a computation, not metaphorically, but literally. If the universe processes information at its core, then the laws of physics might be outputs of deeper informational rules. And if information lies at the root of everything, the idea of simulation becomes less speculative and more like a natural extension of the physics we already observe. Consider quantum mechanics. It tells us that particles do not have definite properties until measured. They exist in a cloud of possibilities. Only when interacting with a system, when observed, do they assume a single state. This is not how classical objects behave, but it is precisely how information processing systems behave. In computing, data that is not used is not fully resolved. Values collapse into specific outcomes only when needed. Some physicists have noticed this parallel and wondered, is the universe conserving informational resources? Does reality render only what must be rendered? This is not proof of simulation, but it is a clue, a quiet one, that our universe behaves with efficiencies that resemble computation. Another clue comes from the speed of light. Nothing can travel faster than this limit. It is the maximum speed at which information can propagate. In computing, every system has a maximum update rate, the fastest speed at which data can move through the network. Some theorists have suggested that the speed of light might be the informational update rate of the universe itself, the speed at which the cosmic processor can communicate between nodes of reality. This is not the language of mysticism, it is the language of physics. It arises from the observation that the speed of light is not merely a property of photons, it is a property of space-time. It emerges naturally from Maxwell's equations and Einstein's relativity. And yet, it also behaves like a computational limit. If the universe acts like a computation, then it could be simulated. If it could be simulated, then the number of simulated universes might vastly exceed the number of physical ones. And if that is true, then, statistically, it becomes more likely that we live in one of the simulated universes rather than the single base universe. This is the heart of the simulation argument, not conspiracy, not manipulation, not overseers watching our every move, just probability. Imagine a civilization capable of harnessing the energy of its entire galaxy, a Kardashev Type 3 civilization. Such a society would have computational power trillions of times greater than anything we can imagine. They could simulate entire worlds, entire histories, entire universes. Not once, but countless times. Every simulation could be as rich and internally consistent as the base reality, with simulated beings who experience consciousness, physics, and time. Now imagine that each of those simulated universes could contain its own advanced civilizations, which might eventually create their own simulations. A hierarchy of realities would emerge, branches upon branches, layers upon layers. Our universe may be one such branch, nested inside deeper levels of structure. To the inhabitants of a simulation, the world would feel real. Their physics would work. Their constants would hold. Their consciousness would arise from the interactions of their matter, whether that matter is physical or computational. This idea is unsettling for some, but peaceful for others. It suggests not fragility, but continuity. A simulated universe is still a universe. A simulated mind is still a mind. Experience is not diminished by the medium through which it arises. Still, the idea raises difficult questions. If we live in a simulation, could we detect it? Some researchers have suggested possible clues, not because they expect to break through to a higher layer of reality, but because simulated universes might carry small fingerprints of their construction. These clues include quantization of spacetime, suggesting a discrete underlying grid limits on energy states, resembling computational precision, unexpected symmetries in physics, as if designed for stability, cosmic rays arriving in preferred directions, hinting at lattice effects limitations in the distribution of high-energy particles, reminiscent of resolution boundaries. None of these clues are definitive, but they are enough to make physicists wonder whether our universe operates on an informational substrate. Another question arises. If our universe is simulated, does it have a purpose? It might not. The simulation could be a scientific experiment, a historical reconstruction, a cosmological model, or simply an emergent byproduct of deeper computational processes. Or it could have no intention at all, just as natural processes in our universe produce complex systems without conscious design. If the simulation hypothesis is true, our universe might be one among billions of simulated environments, each exploring variations in physical laws, initial conditions, or cosmic histories. In this sense, the simulation hypothesis converges with the multiverse idea. Both suggest our universe is one branch in a larger structure. Both suggest deeper realities beyond our own. Both propose that what we see is only a fraction of what exists. The difference lies in the nature of the branching, physical or computational. Yet, even if we discovered that our universe were simulated, the experience of living within it would not change. Gravity would still pull, light would still travel, stars would still burn. Consciousness would still arise from the interactions of matter, whether that matter is physical or informational. If reality is emergent, it remains real. And perhaps this is the quiet comfort within the simulation hypothesis. It does not make the universe smaller. It makes it larger, part of a vast hierarchy of realities, each with its own laws and structures. Still, the deepest question may be this: if our universe is simulated, what lies outside the simulation? Another universe? Another physics? Another layer of rules? We may never know. Our horizon may end not at the edge of spacetime, but at the limits of the computational fabric that sustains it. And as we drift into the next quiet segment, one soft question lingers, gentle and unresolved. If reality is emergent from deeper rules, how might consciousness itself be shaped by those rules? Part 13. Why many universes might be uninhabitable. If a multiverse exists, most universes might never form galaxies, atoms, or structure at all. They may expand too quickly, collapse too soon, or lack stable elements. The fact that our universe supports complexity does not make it special, only statistically rare. We see it because observers can only arise in universes capable of forming stars and worlds. In our daily experience, the universe seems welcoming. Stars shine, planets orbit, molecules bind, life breathes. But this comfort is deceptive. Our universe sits inside an incredibly narrow range of physical conditions that permit any structure at all. Change the initial parameters slightly, and everything collapses into silence. No stars, no planets, no chemistry. Just a universe that expands or collapses without ever forming the scaffolding needed for complexity. To understand how fragile our cosmic conditions are, we must begin with the balance between expansion and gravity. The early universe expanded rapidly after the Big Bang, but the rate of expansion was neither too fast nor too slow. If it had expanded only slightly faster, matter would have thinned too quickly for gravity to pull anything together. No galaxies would have formed, no stars, no planets, just an ever-stretching void of weak radiation. If the universe had expanded slightly slower, gravity would have won the race. The cosmos would have collapsed back in on itself long before stars ignited. There would be no time for chemistry, no time for structures, no time for life. Just a brief flash of existence, and then a return to darkness. This delicate balance was not guaranteed. It emerged from the initial conditions of our universe, conditions that might vary widely across the multiverse. Dark energy provides another example. In our universe, its value is small but positive, causing space to accelerate gently outward. But if dark energy were even a few orders of magnitude larger, galaxies could never form. The early universe would have been torn apart before matter clumped together. If the value were negative, the universe would have collapsed in a big crunch almost instantly. Most universes, if governed by randomly assigned parameters, would fall into one of these catastrophic extremes, expanding too quickly for structure or collapsing too quickly for stability. But the uninhabitability of most universes goes deeper than expansion rates. The formation of atoms themselves requires fine balance. The strong nuclear force must be strong enough to bind protons and neutrons together. If it were weaker, hydrogen would be the only stable element. Chemistry would be almost non-existent. If the strong force were stronger, nuclear reactions would have burned through hydrogen within moments of the Big Bang, leaving no long-lived stars to illuminate the cosmos. Stable stars require precise relationships between electromagnetic and gravitational forces. If gravity were slightly stronger, stars would burn too hot and too briefly. If weaker, stars would never ignite. Stable nuclear fusion, the engine of starlight, depends on a delicate interplay between the forces shaping atomic structure. Even the masses of the fundamental particles must fall within narrow windows. The mass of the electron determines the structure of atoms. The mass difference between the up and down quarks determines whether protons or neutrons are stable. These masses affect the periodic table of elements, the existence of carbon, the chemistry of water, and the viability of DNA-like molecules. Shift these masses slightly, and atoms may never form. Or they may form, but only in ways that prevent long-term stability. In many universes, matter might exist only as featureless clouds of unstable particles, never assembling into the building blocks of complexity. Temperature also plays a role. In some universes, radiation might dominate indefinitely, preventing matter from cooling enough to form atoms. In others, matter might dominate so quickly that it collapses into black holes before any chemistry unfolds. The multiverse, if real, is not a vast expanse of Earth-like worlds. It is a vast expanse of physical possibility. And out of that possibility, most combinations of physical laws produce universes that remain barren. This is not an assumption. It emerges from the mathematics of cosmology. When physicists explore the parameter space of possible universes, the ranges of physical constants and forces, they find that the region permitting complexity is extremely narrow. A sliver, a thin ridge between oceans of uninhabitable configurations. Most universes would be dead on arrival. Some universes would be uniform and empty. Others would be chaotic and violent. Some would be filled with unstable particles that break apart instantly. Others would collapse into black holes before the first microsecond. Only a few, a rare few, permit the slow unfolding of structure, the gentle formation of stars, the synthesis of carbon, the cooling of planets, and the emergence of life. This does not mean our universe is special. It means it is selected, not selected by intention, but by observation. Observers can arise only in universes that allow observers. This idea is sometimes called the anthropic principle, but the term is often misunderstood. It does not claim the universe was designed for us. It simply notes that we can only observe universes in which observers can exist. In a multiverse containing trillions upon trillions of universes, it is unsurprising that at least one would permit life, and that life would inevitably arise within that one. This does not make our universe central or privileged. It makes it habitable, a statistical curiosity in an immense landscape of inhospitable worlds. Some physicists call this the selection effect. Others compare it to winning a cosmic lottery. If enough universes exist, some will inevitably fall into the narrow habitable region. We find ourselves in such a universe because only such universes give rise to beings capable of asking why. Still, the uninhabitability of most universes raises deeper questions about what complexity means. In universes very different from ours, complexity might emerge in unfamiliar forms, not biological, not chemical, but something else entirely. Imagine a universe where dark matter dominates and electromagnetic interactions are weak. Could patterns of gravitational waves form stable structures? Imagine a universe with no atoms, only fields interacting through exotic symmetries. Could complexity arise in those fields? Imagine a universe where time behaves differently, allowing strange, emergent phenomena that do not resemble life, yet possess equivalent intricacy. We do not know. Our imagination is limited by the physics we experience. But even in the broadest view, the multiverse remains a place where most universes are silent. Silent because structures never arise. Silent because stars never ignite. Silent because instability overwhelms complexity. The quiet truth is that our universe's habitability is not normal. It is an outlier, a rare configuration in a vast possibility space. But rarity is not a sign of design. It is a sign of volume. If the multiverse is large enough, rare things become inevitable. And so we find ourselves here, In a universe with stable atoms, steady stars, rich chemistry, and gravitational pockets where matter can accumulate and cool. None of this requires purpose. It only requires probability across a vast cosmic landscape. Yet even this understanding leaves one final question softly hovering. If only a tiny fraction of universes permit complexity, how improbable was our universe's path, and what other conditions might allow complexity in forms we cannot yet imagine? Part 14. How scientists test ideas about universes we can't see. Even if other universes are inaccessible, scientists use mathematics, cosmological simulations, and predictions of inflation to infer their possibility. They look for inconsistencies in our cosmic microwave background, patterns in gravitational waves, and the deep logic of fundamental physics. Testing the multiverse is challenging, but not impossible. It requires precision, patience, and careful interpretation. The central difficulty in studying the multiverse is simple. If other universes exist, they may be forever sealed beyond our cosmic horizon. No signal, no light, no particle can cross the inflating space between them and reach us. And yet, science has always advanced by uncovering indirect evidence, by tracing delicate signatures, by testing predictions, and by eliminating alternatives until one explanation remains. This is the quiet path researchers take when confronting the possibility of other universes. They look for consequences. They ask how the existence of a multiverse might subtly influence the one universe we can observe. And then they search for those influences in the sky, in the equations, and in the behavior of fundamental particles. The starting point is cosmic inflation, the rapid expansion that occurred fractions of a second after the Big Bang. Inflation is not just a convenient idea. It solves real puzzles. It explains why different regions of the universe have similar temperatures. It explains why space appears flat on large scales. It explains why the cosmic microwave background has the particular pattern of fluctuations we observe. Most importantly, inflation predicts something profound. If the inflaton field that drove inflation behaves in certain ways, it will not shut off everywhere at once. It will continue in some regions while stopping in others. Each region where inflation stops becomes a universe. This means the multiverse is not an add-on to inflation. It is a natural consequence of many inflationary models. To test these models, cosmologists look for specific fingerprints in the cosmic microwave background, not direct proof of other universes, but signs that inflation behaved as predicted. These include the distribution of temperature fluctuations, the precise shape of the power spectrum, the uniformity of patterns across large scales, the presence or absence of primordial gravitational waves. Each of these is a test of inflation, and if inflation is confirmed in its more exotic forms, the multiverse follows logically. Inflation also predicts quantum fluctuations that were stretched to cosmic sizes. These fluctuations seeded the galaxies we observe today. By studying how galaxies cluster, how they form filaments, and how matter is distributed, scientists indirectly test the physics of the earliest universe. If the distribution of structure matches what inflation predicts, then the theories that naturally give rise to a multiverse become more plausible. Another tool is mathematics, not as an abstract exercise, but as a way to uncover which frameworks of physics are internally consistent. String theory, for example, predicts an enormous landscape of possible universes, each corresponding to a different configuration of the theory's extra dimensions. Scientists study this landscape not by observing it directly, but by exploring its geometry, its stability, and the constraints it imposes on the physical constants. If the mathematics shows that only certain types of universes can exist, it narrows the field and clarifies what the multiverse might look like. Some researchers use cosmological simulations, running virtual universes on supercomputers, to see how small changes in physical parameters affect large-scale structure. They simulate universes with stronger gravity, weaker dark energy, different particle masses, or alternate inflationary histories. By comparing these synthetic universes with our own, they determine how finely tuned the physical constants must be, and how that fine-tuning may point toward a multiverse. If our universe appears to lie deep inside a narrow band of viable parameters, simulations help reveal just how unusual our cosmos is. If it is unusual, the multiverse becomes a natural explanation. Another frontier lies in gravitational waves, the ripples in spacetime predicted by Einstein. If two inflationary bubbles collided in the early universe, the collision might leave a gravitational wave signature, a faint pattern of distortions imprinted on spacetime. These patterns would be subtle, delicate, almost ghost-like. But with next-generation detectors, such as the Laser Interferometer Space Antenna, LISA, and future terrestrial observatories, scientists hope to search for these primordial echoes. Even if collisions did not occur, the spectrum of gravitational waves can reveal the shape of inflation, and in doing so, reveal whether the models that produce a multiverse are viable. And then there is the cosmic microwave background, CMB itself, our quiet fossil of the early universe. Precision measurements by missions like Planck and WMAP have produced maps of extraordinary detail. Scientists search these maps for anomalies, slight asymmetries, cold spots, or circular patterns that might indicate interactions with other universes. While none have been confirmed, the very search teaches us how to interpret the early universe with greater clarity. The key is not expecting a dramatic signature, but understanding that if the multiverse has ever brushed against our cosmic bubble, the evidence would be subtle. It would appear as a faint deviation, a whisper in the background noise. Another approach comes from fundamental physics itself. Scientists examine the deep structure of quantum field theory, the behavior of vacuum energy, and the requirements of mathematical consistency. If the laws of physics appear to require multiple solutions, multiple stable configurations of spacetime, then the multiverse emerges as the simplest interpretation. Similarly, when physicists study the fine-tuning of constants, they ask whether these values could naturally arise without a multiverse. If no single universe explanation can account for them, then the multiverse becomes a compelling alternative. Even the absence of certain phenomena can provide clues. If we never detect certain particles predicted by single universe models, or if dark energy refuses to fit neatly into our theories, scientists consider whether a multiverse could explain the mismatch. In this sense, testing the multiverse is like testing any scientific idea about things we cannot see directly. We test the theory. We test its predictions. We test its consistency. We test whether it fits more naturally than the alternatives. We ask whether it explains the universe better than any model without it. This approach is how scientists infer the existence of black holes long before we could image them, quarks long before we could isolate them, dark matter long before we knew its nature, gravitational waves long before we could detect them. In each case, indirect evidence came first. Observations confirmed the predictions only later. Many suspect the multiverse may follow a similar path. Still, cosmologists remain cautious. The multiverse is a vast idea, and humility is essential. Some explanations might be wrong, some evidence might be misinterpreted, some signatures might mimic unrelated phenomena. Science moves slowly, not because it lacks imagination, but because it values clarity more than speed. Yet the pursuit continues because the multiverse, if true, offers a coherent explanation for the mysteries that otherwise remain unresolved. The fine-tuning of constants, the structure of inflation, the shape of the CMB, and the deep logic of quantum fields. Testing the multiverse is not about confirming a fantasy. It is about tracing the consequences of our best theories to their natural conclusions, and then asking whether reality aligns with those conclusions. And as we drift toward the final part of this quiet exploration, one gentle question rises. If science can infer universes we cannot see, what does that say about the ultimate limits of knowledge, and how far our understanding may yet reach? Part 15. What the multiverse says about our place in reality. If the multiverse exists, then our universe is not the center of anything, not unique, not solitary. It is one expression of physical laws among many. And yet, within this vast possibility, our cosmic story remains meaningful. The atoms in your body, the stars in the sky, and the galaxies deep in space are still part of a structure with elegance, symmetry, and wonder. The multiverse does not diminish our existence, it expands the canvas on which it lives. The idea that our universe might be one of countless others can feel overwhelming at first. For centuries, humanity believed the Earth was the center of creation. Later, we learned that the sun was just one star among many. Then, we learned that our galaxy was only one island in a vast cosmic sea. Now we confront the possibility that even our universe, everything we can see, measure, or imagine here, might be one bubble among an ocean of universes. Each step has moved us farther from the center, yet each step has also revealed deeper beauty, deeper structure, deeper truth. The multiverse continues that pattern. It challenges our sense of scale, but it does not strip meaning from our place within the cosmos. If anything, it gives us a richer stage on which the drama of existence unfolds. A universe that is solitary can feel fragile, a single moment of cosmic luck. But a universe that is one of many is a universe that belongs to a grander tapestry of possibilities. It is part of a larger structure, a pattern of creation woven into the very logic of physical law. In that pattern, our existence is not an accident. It is a natural expression of a universe with the right balance of forces, constants, and conditions, one of the rare universes where complexity can bloom. Seen in this light, the multiverse does not make us insignificant. It makes us part of something far larger and more profound. To understand this, imagine standing on a quiet shore at dusk, watching waves roll onto the sand. Each wave is beautiful in its own shape and motion, yet no wave claims to be the entire ocean. Each arises from the same physical laws: gravity, wind, fluid dynamics, and each expresses those laws in its own particular form. But the existence of many waves does not diminish the beauty of any single one. If anything, it enhances it because it reveals the richness of the sea from which they arise. Our universe is one such wave. It carries its own structure, its own physics, its own history. It unfolds according to its own parameters. If other universes exist, they too arise from underlying principles, the deep mathematics that shape the fundamental behavior of fields, particles, spacetime, and quantum fluctuations. Those principles are universal. Each universe is an expression of them. This is where meaning enters the story. The multiverse is not chaos. It is not randomness without structure. It is a landscape of possibility shaped by the logic of physics. And our universe, with its delicate balance, its long-lived stars, its galaxies unfolding like cosmic spirals, is one of the few places where complexity can awaken and contemplate itself. In a sense, we are the universe becoming aware of its own potential. The multiverse reframes the question of significance. Significance does not come from being the only universe or the central one or the privileged one. It comes from being part of a system that allows consciousness to exist at all. In this context, our ability to ask questions, to wonder, to explore, to reflect, is itself a rare and precious outcome. Even if countless universes exist, the fact that we inhabit one capable of supporting life means this universe matters intimately to us. It is not generic. It is not interchangeable. It is the universe in which atoms formed stars, stars forged elements, planets cooled, chemistry blossomed, and consciousness eventually arose to ask why. The multiverse does not erase this journey. It does not flatten individual significance. It simply adds a deeper dimension, the idea that our universe is meaningful not because it is isolated, but because it is connected, conceptually, mathematically, and perhaps physically, to a larger architecture of reality. This shifts the philosophical landscape as well. If the multiverse exists, then the story of existence is not the story of one universe, but of many. Not a single cosmic timeline, but countless timelines unfolding simultaneously. Each universe begins with its own conditions, evolves through its own laws, and produces its own patterns. Some remain silent, some produce symmetry, a few produce complexity, and a tiny minority allow beings to think, to dream, to wonder. This does not diminish those beings, it highlights them. It underscores how rare and extraordinary conscious experience truly is. Even in a multiverse with infinite variation, the emergence of sentient life remains a delicate phenomenon. Matter does not easily organize itself into systems that can reflect on existence. Consciousness is not a trivial inevitability. It is a moment of structure emerging from deep physics. In that sense, the multiverse enhances the mystery of our existence. It suggests that consciousness is a late, subtle, improbable flower blooming in one corner of a vast garden. Not because we are chosen, but because we are possible. And possibility in a multiverse is everything. Another way to see this is through the lens of humility. When the Earth was believed to be the center of all things, human understanding was small. As we learned that Earth was not central, our knowledge expanded. The multiverse continues this progression. It invites us toward deeper humility, but also toward deeper wonder. Humility comes from recognizing that our universe is not the only universe, any more than our planet is the only world. Wonder comes from realizing that even amid this immensity, we exist, conscious, curious, fragile, and yet capable of comprehending the laws that shape reality. The multiverse also gently reframes the question of purpose. In a single universe worldview, one might search for purpose in cosmic uniqueness. But in a multiverse, purpose arises from connection, from being part of a larger structure that extends beyond what we can observe. The fact that our universe is one of many does not erase meaning. It reshapes it. Meaning becomes a property of experience rather than of exclusivity. The atoms in your body were forged in stars that lived and died long before Earth formed. Those stars emerged from clouds shaped by quantum fluctuations during inflation. And those quantum fluctuations arose from the deep physics that allowed our universe to form in the first place. In a multiverse, this chain does not end with us. It extends outward to universes we will never see, structures we will never measure, and physical realities we can only imagine. And yet, our existence links us to that larger reality. We are part of its story even if we inhabit only one chapter. The multiverse does not shrink our importance. It expands our context. It reveals that the cosmos is richer, deeper, and more intricate than a single universe could contain. It invites us to imagine beyond our horizon. It shows us that reality is not confined to what we can observe, but extends into realms defined by mathematical possibility, quantum behavior, and the profound creativity of physical law. And in this expanded canvas, our universe remains extraordinary, not because it is alone, but because it is capable of asking these questions at all. As we close this final part of the journey, one gentle truth remains. Even in a multiverse, the universe you inhabit, this one, with its stars, its galaxies, its dark energy, its living worlds, and your very existence within it, is irreplaceable. Your experience of reality is unique. Your consciousness is rare. Your presence is meaningful. And in a cosmos filled with possibilities, that's enough.